All right, so starting with number 2, it would be dy dx is equal to x squared. Wait a minute, am I in the right section? Hang on a second. That's section 3.2. I was like, why does this not look right? Okay, I was looking in the wrong place in my answer book, and I'm like, that's not right. All right, so number 2, the left-hand derivative is 0, and the right-hand derivative is 2 at x equals 1, but it's differentiable at all other points. For number 4, the left-hand derivative is positive 1. The right-hand derivative turns out to be negative 1, but it's differentiable at all other points. Number 6, part A, is all points in the closed interval from negative 2 to 3. B is none, and C is none. Number 8, for part A, it's all points in the closed interval from negative 2 to 3, except for x equals negative 1, x equals 0, and x equals 2. Part B, x equals negative 1. Part C, x equals 0, and x equals 2. Number 10, all points in the closed interval from negative 3 to 3, except for x equals negative 2 and x equals positive 2. Part B, x equals negative 2 and x equals positive 2. And part C is none. Number 12, that is a cusp. Number 14, it is a vertical tangent. By the way, if on 12, if you said it was a vertical tangent, to me, cusps are vertical tangents also. It's just a slightly different kind of vertical tangent, but I would take it. Number 16, a cusp. Again, if you called it a vertical tangent, I would be okay with that. Number 18 is negative 2, and the answer to whatever question they asked was yes. Number 20, oh, does the derivative exist there? Yeah. Number 20, it's negative 3.99999. The answer is yes. 22, 8.000001. And the answer is yes. 24 is 0, but the answer is no. So your calculator lies to you on that one. And 26 is 0, and the answer is no. Number 28, dy dx looks to be x cubed. Number 30, dy dx looks to be tangent of x. Number 32, it's all reals except x equals 2. 34 is all reals. 36, also all reals. Skipping down to number 40, that is true. Number 42 is B, and number 44 is also B. Thus endeth the reading of the answers. Questions?
Did you do number 4?
Yes. So is it about finding the right-hand derivative?
Yes.
Good. If you were asking about the left-hand derivative, I was going to be worried about you. Oops. Let's see, is that on? It's one of my favorite things. All right, so the left-hand derivative is 1, that's not a problem. Okay, so the right-hand derivative, oops. At x equals 1. So that'll be the limit as h goes to 0 from the right of 1 over x plus h minus 1 over h. So far, so good? Okay. So what I would do is I want to clear out the fact that I have got a complex fraction. That didn't work as well as I wanted it to. I forgot that it would also erase the stuff behind it.
That's kind of weird.
Well, there's multiple layers of stuff. So what I would do is multiply both the numerator and the denominator by x plus h. Oh, sorry, 1 plus h. We're doing it at 1. Did you do 1 plus h or x plus h?
I don't really know what I was thinking because I kind of just eyeballed it for whatever reason.
Oh,
And
which is fine if it's a line and you can get the
Yeah.
slope, but if it's not, you're going to have to do some work. So that'll be the limit as h goes to 0 from the right of, when you multiply this, it's going to be 1 minus 1 plus h all over h times 1 plus h. So that's going to be the limit as h goes to 0 from the right of negative h over h times 1 plus h. Dividing the h's and letting the h in the denominator, which is the only one that's left, go to 0. That's going to be negative 1 over 1, which is negative 1.
yeah, that makes more sense.
Good. So you can look out the window and still be engaged.
Yeah. One of those days.
It's okay. All right, what other questions do you guys have? 22, okay. So 22. Find the numerical derivative of the given function at the indicated point using h as 0.001. Is the function differentiable at the indicated point? All right. So you said 28? 22. Okay. So f prime at 2 should be approximately equal to f of 2 plus 0.001 minus f of 2 minus 0.001 all over 2 plus 0.001 minus 2 minus 0.001. You don't have to write it exactly that way, but again, I'm like, it's slope. It makes sense to me. So let's grab our calculator and figure out what these things are. Oh, that's going to be interesting. So clear that, move this over here. So let's clear all of this stuff out. I have no idea what this is. Oh, that was a tangent in a normal line. Okay, so it's x cubed minus 4x. Nope. There we go, minus 4x. And the question becomes, can we do this in a faster way? Well, because we want 2 points, f of 2.001, and we could use the trace feature and do that. I think there's another way. I'm not absolutely positive of this, but let's find out.
Sure, if I'm going to try to tell you one.
I'm sure that he would. So if I go to variables and move over to y variables, And if I do y1, I wonder if you can actually put in something, 2.001. I don't think so. Let's see if that's really right, 0.008. That doesn't seem right, does it? So let's go back to the graph. And let's trace this to 2.001. Was that the number I had? 0.008006? Oh, hey, look at that. So I can actually do this whole calculation on my calculator. I can do, and you can actually get to the variables quicker by doing alpha trace. So y of 2.001 minus y of 1.999. Oops, I need parentheses. Divided by, that's going to be 0.002, right? And there we go.
So do you care if it says we can use a calculator? Can we solve it this way on the homework?
What now?
Can we solve it using the calculator on the homework if it's not grayed out?
Yes.
Oh.
Yeah, absolutely. Okay. Now, you could also, since it was specific about what h to use, I would probably go ahead and do it this way. But if it doesn't, if it just says, find the numeric derivative, your calculator, remember, has that built in. Math H, the derivative with respect to x of, and because I'm feeling lazy, I'm going to go ahead and put in just y1 at x is 2. And it's going to give me the same answer because it uses 0.001. It does that exact calculation. The problem is occasionally, well, the derivative doesn't exist at that point, but it gives you a value.
What value does it give you?
Well, for example, if you were doing, like this one, the absolute value of x minus 3 at 3, that doesn't exist because the left-hand derivative and the right-hand derivatives aren't the same. But it's going to tell you that it's 0 because if we look at what that graph looks like, if you move a little to the left of the point and a little to the right of the point and find the slope, it's going to tell you the slope's 0, even though the slope doesn't exist at that point. It won't always be 0. That just happens to be on some of the easier ones. But the same thing happens on x to the 4/5 power. X to the 4/5 at 0, if memory serve, is one of these seagull-looking things where the derivative at this point doesn't exist.
And that would be a cusp on the sequel, right? Or that would be a vertical tangent.
Tomato, tomato. It's a cusp.
Could you scroll up to number 12?
Certainly.
Because I put that it was a corner.
X to the 4/5. Hey, that was the one you just did.
Okay. So a corner is a perfect ninth, or like a no.
A corner typically is made by two things that look linear when they are joined. The angle is not important. but people typically call this a corner. There are some books that call, like, well, that's a corner too. And I'm like, well, we probably call that more of a cusp. And there probably are some functions. I don't know any of them, but there probably are some that when you zoom in, they still look like this. And other ones, when you zoom in, they start looking more like that. This is your classic cusp. And if that one, when you zoomed in, it started looking more and more like the absolute value function, you would say that it was a corner. What I say is, either the derivative from the left is not equal to the derivative from the right, and then you don't have to worry about, are they going to accept corner this year? Because there's always the chance that they'll be like, nope, we're tired of accepting that.
They don't tell you.
No. So I say it's better to say the derivative from the left is not equal to the derivative from the right, or that the slope from the left and the slope from the right are undefined. And then we're good to go. Now, the one case where I don't do that is where the function has a discontinuity. There I just say the function's discontinuous. But if you have a discontinuity, well, it depends on which kind of discontinuity you have. But yeah, if a function's not continuous at a point, I just say if it's not continuous, it does not have a derivative. Done. All right, any other questions on those? 28? So yeah, it says use ender to graph the derivative of the function. So it's x absolute value of x over 2, and we want its derivative. I wonder what the heck that looks like. So y equals, clear this out. So math 8, the derivative of x absolute value of x over 2. If it's anything other than a very simple fraction, I always use the horizontal fraction bar.
Isn't it 28?
Am I looking at the wrong one? Oh, 28. Sorry. I was looking at 29. It was more interesting.
That's an option. Just make it more interesting.
Yeah, sometimes. So 0.25 x to the fourth. X raised to the fourth, evaluated at x equals x. And I'll do a zoom 6 on it.
You can select the zoom and it just goes right to graphing it?
Yes. If you select the zoom.
I always thought you had to graph it, then go on and change your zoom.
Nope. If you tell it to zoom, it just goes and graphs it. That looks a lot like x cubed. And we can test that by putting x cubed down here. And I'm going to do the follow the ball thing. Yeah, that followed pretty nicely. You can also look at the table, which is pretty convincing. You notice that these values are exactly the same. Okay? All right, any other questions? All right, then let me give you today's notes.
this on Tuesday be calculated?
Probably. Let me look. It will be non-calculated.
Again?
Oh, it has two parts.
Oh.
It has a calculator part and a non-calculator part. And you still need to be able to find derivatives. We're going to learn some rules for finding derivatives today. You still need to be able to do it by the definition. Okay. So here's some rules for differentiation that will make the process much faster. Particularly today, we're going to make polynomials really easy. Now, are you taking AP Physics? You taking AP Physics? No. Okay. So in AP Physics, you've learned the power rule. Okay. So we'll cover that today. So first of all, the derivative of a constant function. If c is any constant, then the derivative with respect to x of that constant is 0. Well, that makes sense. What kind of a slope does a constant function have? No. Well, it does, but what is the constant? 0. A constant function slope is always 0. Okay, the constant multiple rule. If u is a differentiable function of x and c is a constant, then the derivative with respect to x of c times u is c times the derivative with respect to x of u. Now, I think this one makes sense if you think back to algebra where you talked about multiplying a function times 3, for example. If you multiply a function times 3, graphically what happens is the graph gets stretched out. It's 3 times taller than it would have been, right? Well, if you make your graph 3 times taller, won't the slope be 3 times taller? Yeah. So to me, this one makes excellent sense. The power rule. So if n is any real non-zero number, so it doesn't work for x to the 0, then actually it kind of does work for 0.
X to the 0 be 1.
And its derivative then would be 0 times x to the negative 1, which would be 0, except at x equals 0, where it wouldn't exist because you'd have 0 in the denominator. That's where the problem is. So if n is any real non-zero number, then the derivative with respect to x of x to the nth power is n times x to the n minus 1. So you just take the exponent, move it to the front, and then subtract 1 for your new exponent. So the degree goes down 1. And then the sum and difference rules, if you've got two different functions that are both differentiable, u and v, then the derivative with respect to x of u plus or minus v is the derivative of u plus or minus the derivative with respect to x of v. You can just do those independently. The nice thing about this is it lets us do power functions, polynomial functions as well. So, for example, on this one, find dp dt if p is equal to this polynomial function. Well, dp dt would be equal to, for this first term, we can simply use the power function. It would be 5 times t raised to the 1 less than 5 is 4. Then minus, since this is a constant multiple, we will keep it. 6 times the derivative of t cubed, which is 3t squared. plus, for this next part, you can think of it as using the power rule, or you can just go 3/4 t. Well, that would just be a line with a slope of 3/4. The derivative is the slope, so this is 3/4. And then the last part, the derivative of 12, 12 is a constant, so its derivative is 0. And the one thing that students sometimes when they first start learning this, they have difficulty keeping separate is there's a constant rule and a constant multiple rule. Two very different rules. The derivative of a constant is 0. If you have a constant multiplied times something, you keep that constant and take the derivative of what comes after it. All right, so then cleaning this up a little bit, this is 5t to the 4th minus 18t squared plus 3/4.
Do we have to write the first one where you have like the
No.
-6 kind of-
And that's actually what I was going to talk about next is in actual practice, almost no one takes the time to write this out. They just go straight to here. But I want you to be thinking about, well, why is it that we do that? Because what happens is that then when we get to derivatives of things that aren't polynomials, sometimes people are like, why are we keeping that 6? Well, because it's a constant multiple. Okay? All right. Let's move on. Find the location of any horizontal tangents of y is equal to x to the 4th minus 2x squared plus 2. All right. Well, graphically, I'm going to draw this and then I'm going to erase it, but when you have a horizontal tangent, what is the slope?
0.
It's 0. So what we're looking for is, where is the derivative equal to 0? All right, well, I'm not even going to erase that. I like it so much. So dy dx is going to be 4x cubed minus 2 times the derivative of x squared, which is 2x, so that'll be minus 4x. And the derivative of the 2 is just 0. And we want this to be equal to 0. When you're setting something like that equal to 0, show that you're setting it equal to 0. Okay, I occasionally have students who do all this lovely work but never set it equal to 0. On the rubrics on the AP exam, frequently it says, sets it equal to 0. And it's a point. And when there's only 9 points per problem on that, getting that point is important. And occasionally, if you're out of that point and you don't show sufficient work to make people believe that you did set it equal to 0, you can lose the answer point too. Okay? All right, so how are we going to do that? Well, we'll factor it. Factor a 4x out. I'll be left with x squared minus 1. And then factor the x squared minus 1. So either 4x is equal to 0, or x plus 1 is equal to 0, or x minus 1 is 0. So we get x is 0, x is negative 1, and x is positive 1. And I'll just tell you, on problems like this, the most common mistake is that people are so worried about this part that they forget about this part. They leave off the x is 0. Honestly, that's the most common mistake on something like that. Okay? It's important because it gives you another point where this has a horizontal tangent. All right, moving on. So let's say we want to write an equation for the line tangent to the curve y equals x squared plus 3 over 2x at the point 1, 2. Well, the nice thing about this is they went ahead and figured out the y coordinate for us. So we just need the slope. Now, when you have something like this, we don't have a rule for something like that. We'll learn one. It's called the quotient rule. But for right now, we don't know how to do that. But notice we're only dividing by one thing. So we should divide by that one thing and rewrite this equation. So this is going to be y equals x squared over 2x plus 3 over 2x. Remember, you can do that when there is a sum or difference in the numerator, but not when there's a sum or difference in the denominator. If there's a sum or difference in the denominator, you've got to use long division if you're going to do this. So that's going to be 1/2 x plus 3/2 x to the negative 1. And the reason I want to write that last one is to the negative 1 is we don't have a rule for fractions yet. So now dy dx is going to be 1/2 minus 3/2 x to the negative 2. You're like, where'd you get the negative from? By multiplying negative 1 times 3/2. So then the slope of the tangent evaluated at x equals 1. Have I showed you guys this before? This is the evaluation. This stands for evaluated at is going to be equal to 1/2 minus 3/2 times 1 to the negative 2 is negative 1. So my equation will be y equals 2 minus 1 times x minus 1. If this is a free response question, which it won't be on the AP exam, they're not going to ask you something like this in a free response, at least it's unlikely. It's probably going to be in the multiple choice section, and they're going to rewrite it in slope-intercept form. So we'll do the same. So this would be 2 minus x plus 1. So it would be y is equal to negative x plus 3. Okay, any questions about that? All right, next example. Find the points on the curve where y equals the polynomial function 0.2 x to the fourth minus 0.7 x cubed minus 2x squared plus 5x plus 4, where tangents to the curve are horizontal. And this is a calculator problem. Okay, that does not mean graph and estimate, which I've seen students do. And you get kind of close, or can, and it also doesn't mean, oh, I'm using a calculator, I don't have to show any work. Doesn't mean that either. Okay? So if I want horizontal tangent lines, I want to know where is the derivative equal to 0. So I've got to find the equation for the derivative. So this is going to be 0.8 x cubed minus 2.1 x squared minus 4x plus 5, and I want that to be equal to 0. This is one of the 4 things that you're expected to be able to do on the AP exam using your calculator. So 0.8 x raised to the third minus 2.1 x squared minus 4x plus 5. Before we even graph this, what is the most number of zeros that this function can have? It's a cubic function. Therefore, it can have at most 3 solutions. What is the least number that it can have? Think about the graph of a cubic. It looks something like that. It can, if it could have 1 if it's, if the x-axis is here or here. It could have 3. Could it have 2? Yeah, it'd have to have a double root. Right, but so it's either 1, 2, or 3. It's important to kind of think about that before you start graphing it, because sometimes you're like, oh, I saw 2, and you're like, and neither of them was a double. Well, then there's got to be a third someplace. So I will just graph this because I know that I was in the Zoom standard already. 1, 2, 3. Oh, wasn't that nice? 3 easy to see ones. So we'll calculate the zeros of this function. The first one is somewhere between -3 and -1. I don't like to just hit the arrow key over and over again. I'm too lazy for that. I'll make my left bound -3 and my right bound -1. And just hit enter when it tells me to guess. Then I don't have to do that. 3 decimal place accuracy at a minimum. And then we'll just keep doing that. Calculate the 0. This next one is somewhere between 0 and 2. X equals, wow, that's really close to 1, 0.948. And then we'll do it one more time. Calculate the 0. This last one is between 3 and 4, looks like. And we have x equals 3.538. By the way, on that one, if you round it to 3.539, that's fine. You can either truncate or you can round. I think I may have told you guys the story. Aaron Barcio was in my class several years ago, and it drove him crazy, especially on one like that, if I truncated it. Because he's like, but it's an 8. It really should go up. And you're like, not if I don't want it to. All right.
That sounds like a very much a you and Aaron Barcio story.
It very much was. All right. So here's an important thing to know. While the derivative of a sum and the derivative of a difference is the derivative of the individual parts added or subtracted, you can't do that with a product. It will not work in most cases. There are a few oddities where it does work. But take, for example, if I was going to take the derivative of x to the 5th, that's 5x to the 4th, right? Do you agree that x to the 5th is equal to x cubed times x squared?
Yeah.
And the derivative of x cubed is 3x squared, and the derivative of x squared is 2x. If we multiply those together, we get 6x cubed. Is that even close to 5x to the 4th?
Kinda. You're just one off on me.
The degree is off.
Yeah.
That's an order of magnitude. That's bad. Okay? What we can do, however, is use the product rule. And the product rule says that if u and v are differentiable functions of x, then the derivative of u times v is equal to u times the derivative of v with respect to x plus v times the derivative of u with respect to x. Now, a note here, if u times v simplifies easily to a simple function, do the multiplication first, right? You wouldn't want to take the derivative of this by finding the derivative of x cubed and the derivative of x squared. Now, just to show you real quickly, it does work. If we took the first part, so x cubed, times the derivative of the second part, which is 2x, plus the second factor, x squared, times the derivative of the first, which is 3x squared. You get 5x to the, excuse me, you get 2x to the fourth. Sorry, I was skipping ahead a step. Plus 3x to the fourth is 5x to the fourth. And basically what's going on here, you may be going, well, what the heck is happening? Well, think about it this way. If you're multiplying two quantities together, you can think of that as a rectangle, right? And if this grew a little bit, what's going to happen is the little bit that it grows this way is multiplied times this width. And the little bit that it grows this way is multiplied times this length. So you can think of it in terms of a rectangle like that. The growth of the rectangle is this full width times how much the length got bigger plus this full length times how much the width got bigger. Okay? All right. So, page 3. Now I'm curious, what's on page 4? Oh, yeah. We have a lot of stuff going on here today. So here they want us to find the derivative two ways, by multiplying first and then by using the product rule. Okay. How are we fixed for time? 8:42. Oh, we are just about out of time entirely. Interesting. Hang on just a second. All right, we're going to skip this one because of time. I apologize. We will come back and do it tomorrow in class. So then the quotient rule is if you have, you're dividing two functions. So you would take the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator over the denominator squared. So again, if you can do the division first, it's usually a lot easier if you'll do that. All right, we are going to do this one with the quotient rule. So here, y prime, if we do it using the quotient rule, we keep the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. From here, it's just a matter of simplifying that. That's 4x squared minus 2x squared. Be sure to distribute the negative, minus 6 over 4x to the fourth.
And for the numerator, you're using the derivative of it, right?
What?
For when you're putting like the 2x.
So I take the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator.
Okay.
So this ends up being 2x squared minus 6 over 4x to the fourth. I would factor out a 2 and cancel it out everything so that that's x squared minus 3 over 2x to the fourth. We could also have done this by doing the division first. Okay, the bell's going to ring any second, but let me just show you that you can take the derivative over and over and over again. Okay, I apologize, I didn't realize the notes were quite this long. I would not have gone on so long about some things earlier in class. But y'all have a great day, and I'll see you tomorrow.